can start now. Okay, guys. So good afternoon, everybody. Again, at any time, if the voice is not clear, just let me know because I don't know, right? If the voice is not clear, I have no idea. Anyway, I wish if I can know, but I don't know. Okay. Anyway, so today I'm gonna start a very interesting topic, very important, very interesting. This topic is called interrupts. Okay. So as you see here, guys, first I'm gonna explain what is interrupt. So I'm gonna make a definition. So what do you mean by interrupt, right? Then after that, I'm gonna explain how we program interrupts. Okay. And then, as I'm gonna say, right, as I'm gonna explain right now, guys, there are different sources or different types, whatever you wanna call it. It's better to use the word source anyway. So there are different sources of interrupts. Okay. So in this chapter, I'm gonna explain two sources of interrupts. One is called IRQ, the other one is called RTI. Okay. The good thing is, if you understand this section 4.2, okay, you can program any source of interrupts. This is a good thing because the way we program one source of interrupt is almost identical to it was just very small changes. Okay, so if you know how can you program one source, if the other sources are almost the same. Okay. Anyway, so let's start with the definition. So what is interrupt? What do you mean by interrupt? Okay, why it is good? Is that good or bad or whatever? Okay, it's something very great, very good. You will see right now. Okay. Anyway, so let's read the definition here and try to understand every single word. Okay. So an interrupt is an event, okay, that requests the CPU to suspend. Look at the words, guys, please. Event to request the CPU to suspend the program execution briefly and run a subroutine. This subroutine is called interrupt service routine. Okay, so what this means? It means, okay, number one, we have event. It's not clear yet. What do you mean by event? Okay, what do you mean? I'm gonna elaborate. But for now, interrupt starts with an event, and this event should request the CPU microprocessor to suspend the program and execute as a response. As a response to the event, the CPU has to execute a subroutine. This subroutine, we call it interrupt service routine, right? So, and usually what you in this this is a routine, subroutine, right? Usually, or what we have to write here in the subroutine is something you want to do as a reaction to this event. So there is an event, and because of this event, I want to do something, right? So this is what you have to write in the subroutine, okay? In other words, let me say it in a different words, okay? In other words, every time there is an event, the subroutine is executed. Please say it again. Every time an event occurs or an event is triggered, every time there is an event, the subroutine is going to be executed, okay? So you have to write the code. So it's up to you. Now what do you want to do? If there is event coming to the CPU, okay? So what do you want to do? Just write the commands in the subroutine, okay? So and then after executing the interrupt subroutine, the CPU resumes the program execution from the point it left the program. Okay, so let me elaborate more to fully understand the concept or the idea here. Assume this is our program, guys. That's what we used to do. We have move instruction, load instruction, add instruction, store instruction. That's what usually we do. Is that right? Now, I told you before, after we execute move, the CPU is gonna come to next instruction, right? And after executing this instruction, the CPU is gonna go to next instruction. After executing this one, CPU is gonna execute next one, and so on, right? This is true only if there are no interrupts. Because what happens is, now this is the full picture. Now, this is the full picture. After executing every instruction, right? The CPU may go to next instruction, right? Or it may, if there is interrupt, it may go execute interrupt to respond to the interrupt subroutine and come back here. For example, so after executing this instruction, there is no event, because no event, there is no request. Because there is no request, after execute this instruction, we're gonna execute next one, right? Now, after the CPU finished this instruction, right? Now, no interrupts, no event, so it's gonna go to next one. Now, after executing this instruction, what happened is there is an event. So an interrupt is requested. So CPU is not gonna go to load. CPU is gonna respond to this event to go execute a subroutine. We call it interrupt subroutine, and then after that, it's gonna come back to here. Is that okay, guys? You understand the concept? You understand the idea? Okay, let me again say it also in a different way so that you fully understand it, okay? So, based on what one student can say, okay, look, Dr. Mahmoud here. Based on my understanding from what you explained, it looks like you are calling a subroutine. That's what we did when you call a subroutine. Yes, I can say yes. It's similar to calling a subroutine. But there is one big difference. What is the big difference between calling a subroutine we did before and between this one interrupt here? What is the big difference? The big difference is to call a subroutine, you have to write an instruction to call a subroutine, jump subroutine, branch subroutine, as we did before, right? But here, if you look what I did here, I didn't write an instruction to call a subroutine, right? I didn't do it. So who is calling the subroutine? As long as you didn't write an instruction to call the subroutine, the event. You got what I'm saying? So once the event comes, CPU is gonna suspend your program, it's gonna go execute the subroutine and then come back to here quickly. Okay, guys? Any question? So as I'm saying here, no command to call the subroutine. Don't be confused. Okay, this is a main difference between a subroutine and interrupt subroutine, right? So the subroutines I explained before, guys, right? You have to write an instruction to call the subroutine, right? But here for the interrupt subroutine, you don't write an instruction, but it's hardware. It's a calling. The hardware is gonna call it. I'm not gonna write an instruction. When event comes, the CPU automatically is not gonna move to next instruction, but go execute a subroutine and come back to here. Okay, guys? And as I'm gonna explain, for sure, until now you shouldn't. It's not clear what do you mean by event. I'm gonna clarify it, so don't worry about that. So there is something called event, right? But I'm gonna tell you what is this, right? And this event, as I told you, it comes from multiple sources, right? So it's not only one source. That's why we have multiple interrupt sources, right? So multiple sources can trigger interrupt, not only one. And each source should have a different subroutine, right? So it's not only one subroutine, actually. It's multiple subroutines. So if event one happens, the CPU is going to go execute the subroutine of event one. If event two happens, the CPU is going to go execute the subroutine of event two, and so on. Is that okay? Okay. And then, okay, again, as I told you, here inside this subroutine, you should write whatever you want to do. Okay. So when an event happens, what do you want to do? Just write here the instruction here in the subroutine. Okay. An interrupt means, as I said, an event has occurred, so there is an event, and a relevant action should be taken, right? So I have to react to this event. How you react to this event, this is what you have to write here in the, this is the instructions I'm gonna write here. Every time there is an event, a subroutine is called. That's it. Every time there is an event, a subroutine is called. Is any question, guys? Please, if you're still confused, again, I know maybe I'm repeating, I explained in a different way because it's very important to understand the concept, because this is a very important concept. If it's still not clear, please, I'm gonna clarify more anyway. So let me continue, and then you can just hold your question now until I finish this small section, and I think everything will be clear now. Okay. So now, Look here, guys. So what do you mean by event now? Okay, an event can be a signal coming from a device such as sensor, circuit, timer, or whatever. Okay, for example, this is a microcontroller here, guys. There is one pin here, one pin. All right. So this pin is connected to a sensor, right? So this sensor should sense a train. I'm just giving you example to understand what I mean by event, right? So what I'm saying, every time the sensor senses senses the train, right? So the sensor make a pulse like this one. When this pulse comes on the pin here, on the pin of the microcontroller, actually this is the event I'm talking about. So this is an event. Every time the train comes, the sensor should trigger interrupt by generating a pulse like this one and put it on the pin here, external pin. Once the microcontroller, right, receives the signal, the hardware. So so now there is an event that is requesting the CPU to suspend the program, right? So what's going to happen? The CPU is going to leave the program, the main program, right? And then it's going to go and execute a subroutine related to this event and come back, right? So let me ask you a question. In this specific example, what should I write here in the interrupt subroutine? As I told you, what I have to write in the subroutine here, guys, is a relevant action to the event, right? So in this specific case, we have a train, right? So what should I write in the subroutine? So yeah, so what I have to write in the subroutine, for sure, I have to close or I have to lower the gate, right? So because the train is coming, right? So that's what I mean, event and reaction, right? So a sensor outputs a pulse when the train approaches a crossing. The signal requests interrupt, and microcontroller runs the relevant interrupt routine that should lower the gate, right? Usually, also one expression we are using, guys, like the word serving. When I say we serve the interrupt, serve means execute its subroutine. So if there is an interrupt, right? if if I say the microcontroller is serve this interrupt, or is gonna serve this interrupt, so we use the word serve. So serve an interrupt, it means execute the subroutine. So we use this term. This is the term we use. It's like, you remember in stack, when I explained in stack push and pull, okay, instead of read and write. This is the term we use. The same thing here, serve. So if microcontroller is going to serve the interrupt, that means it's going to execute the subroutine. Okay, guys. So this is an example for an event, and then you have to take action. Okay, let me elaborate. Now I want to explain here, guys. Okay, so yeah, so now you give us definition. Now we understand what is interrupt. You told us event and the subroutine. Yes, event, and because of this event, the microprocessor is going to suspend the program. We are gonna run a subroutine, and I have to write here the code. In this code, whatever I want to do when the event happens, that's what you told us, right? So, but is that useful? Is this interrupt useful? 100%, 200%, 500% useful. Okay, guys. Interrupts are extremely useful. Okay, without interrupts you cannot make real application. Without interrupts you cannot full benefit from the capability of the microcontroller, right? So interrupts should enable us to make like a big application, right? So microcontroller, you can have a keypad, you can have LCD, you can have a sensor, so you can run a lot of things at the same time using interrupts. Let me clarify it more, right? So here, just so what I did so far, guys, I make just a definition in a couple of slides. I made a definition for what is interrupts, right? Now I'm gonna focus on, okay, why are interrupts used, or how they are useful, or how we're gonna use them. Okay, that's what I'm gonna explain right now, and then so let me explain it. So number one, guys, why are interrupts used? Okay, number one, or why they are beneficial or very important. Number one, better utilization of CPU, of the capability of CPU, right? That means we can program big application. Remember, guys, the CPU, or this chip, the microcontroller, it can do a lot of things. It's not For sure, I know in chapter 3 we did very simple things like flashing, turn on and off. For sure, I'm not gonna buy CPU so that it is all the time is gonna do flashing, right? No, CPU you can create a system. You can create like a big system, right? You have a camera, you have a sensor, you read something, you send something, so you can make big system. Okay, so let me elaborate. What do you mean by better utilization of CPU because of the interrupts, and how? Is that a magic? No, it's not magic. I'm gonna explain it how, right? And how this can be used to program big application. For sure, I'm gonna explain now. Okay, let me give you very specific example now, guys, just to understand how interrupts can help us to better utilize or make big application. Let me. So, for example, if I want to make a delay, as we did in chapter 3, how we created a delay in chapter 3? You remember delay YMS. That's what we did in chapter 3, right? So in delay YMS, CPU executes some commands. Actually, these commands are not doing anything. You remember, right? When I explained push pull, I was just wasting time, right? So that the execution time of these commands is equal to the delay. That's what we did in chapter. So this is not the best way to do that. Why? Because I'm wasting the CPU capability. What do you mean exactly? Because the CPU is tied. Tied. Why? What do you mean by tied? I mean, if there are other things, so because we use the CPU only for one task, right? Just you just executing some instruction, right? So that to create a delay, right? What if there are some sensor? What if there are you want to receive data, you want to send data? What if you want to use the keypad? What if you want to use other things? You cannot. Why you cannot? Because the CPU is busy all the time just to execute instruction, right? That is why I'm wasting the CPU capability. Okay, but if you don't do that, is there a better idea? The answer is yes. So what is the better idea? Using interrupt. So what this means, I'm gonna tell you what it means. Look here, guys. I'm gonna just elaborate now. Look here. Instead of counting or making the delay by the CPU itself, right? That's what we did in chapter 3. The CPU just running commands. These commands are not doing anything other than just we are counting for 1 second or y millisecond as we did. And instead of doing that, no, we're gonna have external circuit because nothing is for free. If you wanna create a better system, I have to add some external circuit. Okay, so here I did external circuit. I can put here a timer, right? And instead of asking the CPU to count or to execute an instruction to make y millisecond, no, the CPU can just tell the timer, please timer, interrupt me after y millisecond. And now the CPU is free. You got the idea? So now the CPU is free. I can execute other instruction. I can take care of the keypad. I can take care of the sensor. I can execute anything else. You got what I'm saying? Because the CPU is free now, right? Because the counting for the time is done by external circuit. And when the time expires, after y millisecond, this timer is gonna interrupt the CPU. It's gonna send signal CPU, right? CPU, this is the time now, and now it's y millisecond. You got what I'm saying? So this is if you use interrupt, okay? So periodic interrupts can be generated by timer at a regular rate. So, and that's what we are gonna do in this chapter, by the way. What this means? It means I can ask the timer, please timer interrupt me every 10 milliseconds. Please timer interrupt me every 100 milliseconds, and so on, right? And the good thing, the CPU does not need to count for the time. Counting for the time is going to be done by external circuit, and by this way, I can do. This is the look, guys. The sentence I'm going to say right now is the most important sentence. Please listen to it carefully. And if you have any question, don't be shy to unmute and talk to me. I'm here to help you. I will be happy if you understand the topic and you love it. Okay, so don't be shy to. So listen to everything I'm going to say now. So the main idea now is. I can do the same task, delay, right? So I can create a delay, but I'm going to take a very little time from the CPU. I'm going to take a little time from the CPU. This is the most important thing, right? Why little time? Because the CPU has to go and write. It has to sit. I have to execute a couple of instruction to set the timer, to tell the timer, please timer interrupt me every y millisecond. Is that okay? And then when the timer interrupts me every y millisecond, I have to do action like turn the LED on, turn it off, or whatever. By this way, if you compare this idea to what we did in shop without interrupts, when the CPU spent all the time just to count for y millisecond, right? For sure. So this is much better, because this idea using interrupts, you are going to take little bit, or so sorry, less time. You are going to take less time from the CPU, so that the CPU can do other things. This is the main thing. That's why we are looking for interrupts, because of interrupts I can run multiple things at the same time. This is the main thing. That's how we can create big application. Let me give you another example here, guys. Again, I'm just wanna you fully before I explain how you program, you should understand the concept very well, right? So let me tell you, if I ask you to do something like that, just again here, I just wanna you to understand again how interrupts can help us to make big programs. All right. So that's why here I created this example, so that you can realize it or understand better, right? So let's see here. Write a program to repeatedly turn on an LED for 1 second and turn it off for 1 second, flashing. That's what we did before. Okay, that's we did flashing LED. So now I want to write a program to do flashing LED. Also, read the keypad and display on the LCD. This is the lab you will do, is reading from the keypad, displaying on the LCD. This is the lab you are going to do this week or after tomorrow. Okay. So anyway, so what I'm saying, not after tomorrow, so Thursday. Okay. Anyway, so what I'm saying now, I want to do two things at the same time. I want to do flashing. Also, I want to read the keypad and take one value from the keypad and display it on the LCD. Right. Let's see here. If I don't use interrupts, right? So how I can do that? Look here. Here I'm gonna, for example, begin, turn an LED on, wait 1 second, turn an LED off, wait 1 second, repeat, right? So now the CPU is busy all the time, right? So can I run the other task here? It's like what I'm explaining here, guys. I have two tasks. I want a microcontroller to do two tasks at the same time, right? One task is flashing an LED. The other task is using the keypad and LCD, right? If I write something on the keypad, I want to see it on the LCD, right? So if you don't, if without interrupts, can I do the two tasks at the same time? The answer is no. The answer is no. Why? Because this task, the flashing is gonna take 100% of the CPU, right? Remember, we don't have multi-core here, right? We don't have multi-core. We have only one processor. This processor can execute only one instruction at a time. At a certain time, it can only execute one instruction, right? So here, so that means only one task is a flashing. This flashing can only can only take one. This task can take all the time of the CPU. So I cannot add another task because the CPU is already busy all the time, right? That's why without interrupts, I can do very limited things. Now with interrupts, listen, look here. I can, in the main program, now I have two tasks, guys, right? So in the main program, I can put the code for keypad and LCD. So in the main program here, once you enter some value in the keypad, I'm going to display it on the LCD. Is that okay? Also in the interrupt subroutine of the timer, assuming this timer is triggered every 1 second. So I'm gonna ask the timer, please timer interrupt me every 1 second. Is that okay? So what's gonna happen? So I'm all the time I'm here. The CPU is here all the time. Every 1 second, I'm gonna go. If the LED is on, I'm gonna make it off. If it is off, I'm gonna make it on and then come back. You got what I'm saying? And then every 1 second, I'm gonna go. I'm gonna change the status of flip LED, come back. Every 1 second, go, flip, come back. You got what I'm saying? So by this way, I can do two tasks at the same time. Not only that, guys. I can do three. I can do 4, I can do 5, I can do 6, I can do 7 tasks. How? Again, this is the main program. Go, execute, come back. Go, another, if there is another source, I'm gonna explain later, come back. Go and come back. Go and come back. You got what I'm saying? Someone can ask me, but again, when but you told us the CPU is gonna suspend this program. Yes, that's true. Again, keep in mind, our microcontroller can only execute one instruction at a time. We don't have multi-core. We don't have multi-core processor, guys. So it's not like multiple processors. It's only one processor. So our microcontroller can execute one instruction at a time, right? So if the microcontroller executes this one instruction, so it has to suspend this one. If the microcontroller is here, so it cannot do this one. So it has to be only in one place at a time. Okay. So someone can, but you told us you are gonna suspend this program, right? And do this task. Or and also not only that, you told us I may have another task 2, task 3, task 4, and task 5, right? That means I can be here, I can be here, I can be here, I can be here, right? But and you are gonna suspend this program. That's what you told us. So that means when I press a button in the keypad, it might not work. You understand what I'm saying? Because the program is, so the CPU is not going to be responding, not responsive, right? Because when I press a keypad, you are not going to see it on the LCD. Let me tell you my answer. My answer is no. You will feel, you are going to feel all of them are running at the same time. You know why? Simply because microprocessor is very fast. You are not going to feel it. Why? Because just a couple of instructions here are gonna take how will they may take less than 1 microsecond. You understand the point? So 1 microsecond, you are not gonna feel it, right? Just by the time you press the keypad, this is gonna take more than 10 milliseconds, right? So I'm saying just 1 microsecond. That's why I'm saying you should understand the CPU, guys, is capable to do a lot of things, is capable to run multiple tasks at the same time. And the way we do it, right? Actually, it's not very accurate to say we run multiple tasks at the same time. Actually, you run one task at a time, right? This is the reality is, right? However, or we only in one place at a time. But because we do it very fast, you are gonna feel everything is running is smoothly, is smoothly. Okay. So again, so you are gonna go fast and come back. So you are gonna once you press a button in the keypad, you are gonna see it on the LCD. You are not gonna see any delay or irresponsiveness. So processor is gonna be responsive, right? Also, the LEDs flashing nicely. If you have another task, it's going to be nicely, and so on. This is, again, hopefully you understand. I spent a lot of time just to try to convince you how interrupt is. It's a new concept, a new idea. It's how it is very. So this is the main point again, guys. Look here. Again, we have only one processor, right? So what happens, this program here, it took 100% of the time of the processor, right? No, now it's not like that. This one is gonna take little bit time from the processor. This one is gonna take little bit time from the processor. Also, if you have another tasks here, if you have another tasks, every task should take little bit time of the processor. You got what I'm saying? If someone can tell me, what if I write too much code here? What if I write too much code here and this task takes too much time, right? For sure, this will impact the other tasks. This will impact we don't do magic, right? We have only one processor, right? So if you write here too much code, and usually this is not the case, I'm going to tell you why. Okay, but for now, usually this is not the case. So you have to go and do something very quick and come back. But if you write too much code here, right, or if the processor spend too much time here, this will affect for sure now you may feel that the keypad is slow, right? But usually it doesn't happen this way. You know why? I'm gonna tell you why. Because some work was already done by the external circuit, that like counting for the time, right? CPU is not gonna do that, right? So this is something like I delegate this task to the external circuit, right? So just I'm gonna go and flip LED. That's it. So I'm not gonna do counting because there are some hardware circuit external circuits that helps me. Okay. So anyway, let me give you another example to understand also why interrupts are important. They are very interesting before I finish this part, and then before I go to programming, right? How you program it. But before programming, number one, that's why I spend a lot of time, and sometimes I repeat, because if you don't understand the concept very well, because this is the foundation, I'm gonna build on this foundation. So if you don't understand the concept very well, uh, it's gonna be problem to it's gonna be difficult to understand programming or how can use interrupts. So let me give you another example, guys, to understand why interrupts are again why interrupts can help me or can enable me to write big program, can do multiple tasks at the same time, right? Again, this is because I'm not going to take too much time from the CPU. Every task is not going to take too much time, right? So because of the interrupts, because the external circuit is going to do some work, right? So here, as I told you here, counting for the time is not going to be done by the CPU. This guy is going to help me, right? So this guy is going to do the counting instead of doing it by myself. So it's going to help me, right? So let me give you another example. Another example here, guys. I told you I have a sensor. I want to sense as a train, right? If a train is coming, I have to lower the gate. Okay. So if I want to do something like that without interrupts, right? How I can do it without interrupts? That's what we call bowling. Bowling. Okay. Again, this is also a very important term in computer engineering. You should understand what bowling means, right? So let's see what bowling means here, guys. Okay. To avoid missing an event here, the word event means the train is coming, right? This is what I mean by event, right? So to avoid missing an event, the CPU must continuously, right, read the sensor pin. I saying again, I'm saying without interrupts. So I have a pin. We have a pin here. So the CPU, I have to make like a loop. I have to check. Are you one? I have to ask continuously. Ask the pin. Are you one? Because if there is a train, this one should be one. Are you one? No. Are you one? No. Are you one? No. Are you one? No. لو قال if it says to me yes, I am one, so I have to go and lower this one, right? So I have to continuously read the sensor pin, so the CPU cannot do anything else. I need 100% of the time of the CPU, right? That's why I cannot create big programs. CPU all the time has to continuously to check the pin, right? For sure, this is wasting of the capability of the CPU, right? So sensing and to controlling other devices, I cannot do this. So if you have like here, if you want to, usually CPU is used, or microcontroller is used if you want to create a system. So you don't only have a sensor and just a gate. No, you may have a LCD, may you have another sensors here, maybe you have a buzzer. So you want to take care of, you have to run several things anyway. So if already the CPU is just busy all the time just to read the pin, okay, I think I'm here. Look here, guys. Without interrupts, I have to do this way, right? I'm gonna say, if the sensor pin is one, lower the gate. If no, just to go back and repeat. So I have to continuously check. If I don't do this way, if I don't continuously check, I may miss. I may miss a pulse, right? I may miss a pulse here or miss an event, right? Now, so this is without interrupts. With interrupts, we can make something very uh, fantastic, wonderful, right? What is this? I'm gonna tell you here. CPU, okay. I'm gonna the CPU. I'm not gonna check. The CPU is not gonna check, right? So what's gonna happen? I'm gonna ask the sensor, please sensor, right? Pay attention to the trains. If you can see a train coming, please interrupt me, right? So now I can do something else. I don't need to do this task by myself, right? So here the CPU, I can do something else, right? And once a train comes, this sensor is gonna trigger interrupt, or is gonna make event to trigger interrupt, and now the CPU is gonna leave what it is doing right now, right? Another task just to lower this one, okay? So this is called booling without interrupts, frequently checking. So booling means you frequently or continuously check an event, right? So here we have the interrupt circuit will notify the CPU when there is an event, right? So booling wasted the processor resources in checking infrequent but important events. Please read this sentence, guys, right? So continuously check. I'm just losing the CPU because I cannot do anything. The CPU just, yeah, it's checking infrequent but important events. Okay, so here I give you example here, guys. So without interrupts, as you see here, the CPU is busy all the time, right? But with interrupts, no, the CPU can do something else here. I'm free all the time. And then when there is interrupt, I'm gonna go, okay, lower the gate and then come back and so on. Maybe have another task here, maybe have another task here, every and from another interrupt source. So here this is the main program. So I'm the main program. Once interrupt is coming from one interrupt, I'm gonna go execute the subroutine quickly, come back, go execute the subroutine quickly and go back. Okay, so the CPU continuously checks the sensor bin because interrupt can be triggered at any time. I'm talking about this case, right? CPU should not do anything else to avoid missing the event. Again, I'm talking about this case. But here, no, I'm not gonna bother myself. The interrupt is gonna trigger me, and automatically I'm gonna suspend the program, go do something and come back. Okay, guys. So that is how we can do multitasking. Multitasking. You can do multiple tasks. They look they look as if they are the same time, but actually you run only one task at a time. But because you do it very frequently, you do it very fast, you feel like everything is done. You run multiple tasks at the same time. Okay, guys. Any question here, guys? Please, before I go to how can you program it. Any question here about the concept? Anything I need to clarify here? You in the definition or why? Yes. Yeah. Go ahead.
Oh no, I was gonna say we're all good. I'm ready to see how to code it.
Okay. Okay, guys. Is that clear? Okay. Now, so now the conclusion is, let me just write something here. I wanna wrap up this part so that I can start the other part programming wise. But okay. So now, guys, the idea is that you are gonna have multiple tasks. For example, this is now our programs are gonna be different from what we did before, right? So what we did before, guys, main program. So in the main program, guys, you used to write something and you can have subroutines here as well. All of this, we call it the main program, right? So even if you are in subroutine, now, this is what we did so far, okay? Now, your program is going to be different, right? Why? Because you used to write your code only in one place. This is just one place, right? Now, if you use one interrupt one, for example, okay, you can have interrupt two, you can have interrupt three. For sure, I'm gonna elaborate later. So now your program can be written in multiple places, right? So and I can here put here like task one, right? You can put here task two, and you can put here task three, and you can put here, for example, task four. You got what I'm saying? And what happens every time there is interrupt, go execute and come back, go execute and come back, suspend this one and go and come back. And if everything is running fast, you will feel like all of them are running at the same time, which for sure is not true. But you are not gonna feel that anything is suspended. Everything is running smoothly. You got what I'm saying? And now the programming problem, guys, I'm gonna give you, not again, what we did so far in chapter 3. I give you only one task. What we did so far in chapter 3, right? I give you one programming task. uh, Make flashing, just read the keypad and send some value to the LCD. This is one task, right? Starting because of interrupts in the programming problem, I can give you multiple tasks. For example, task one, for example, the keypad and LCD. For example, task two, right? For example, flashing. Okay. Task three, you have a sensor, right? You read a sensor, and then like alarm sensor, whatever, alarm, fire, whatever, okay, security sensor, whatever. So you have a sensor should receive some alarm, and in case of emergency, you may also need to make a alarm buzzer. You need to run the buzzer. So now you have multiple tasks, and now you need to decide. It's like you need to manage your program. Should I put task one here, or you use task one here, or so you need to make some kind of management. So where now you have multiple tasks. So usually we put one task in the main program. Usually we put one task in every interrupt source. Okay, so for sure we have many sources. Okay, as I saw, interrupt sources. So the good thing is, programming wise, it's just, look, I spent a lot of time to just in the concept. This is a very important thing. You know why? Because in programming, nothing almost new in programming. It's not nothing new. So, and the good thing, as I said, once you know how to program one, all of them are the same. You just change some numbers, right? So as I'm gonna elaborate now. So in this chapter, I'm gonna explain two interrupt sources in but there are maybe 18, 20 sources. Okay, anyway, so let's now talk about how can you program them. Number one, look here, guys. We have, for our microcontroller, we have two types of interrupts. One is called maskable, and another one is called non-maskable. You can tell from the English name, maskable, non-maskable. So what this means? Very easy. Maskable means, the word maskable means, it means you can turn on or off, right? So you can turn off. This is the meaning of the word maskable. Non-maskable means you cannot turn off. It has to be on all the time. Oh, that means that, okay. Or on or off, or you can disable or enable. Okay. So tell me if I have interrupt source, right? One source of interrupt, and then I disable it. What this means? I'm gonna tell you what it means. Okay. So I have interrupt source, for example, interrupt source number one, right? And you told me if it is maskable, it means I can disable it. Disable, or you can enable, right? But you told me for this interrupt, it is enabled all the time. Yes. Okay. So what it means if you disable interrupt, what it means? It means, look here, guys. Again, what is interrupt? Interrupt means every time there is an event, I'm gonna run a subroutine. Interrupt subroutine. That's it. And this operation, it's called, we serve the interrupt, or the microprocessor serve the interrupt. Serve it, right? So every time there is an event, right, you run a subroutine. That's the meaning of interrupt, right? However, if the interrupt is disabled, if you disable means you turn it off. Simply, if you turn the interrupt off, that means even if there is an event, right, we're not gonna run the subroutine. So I'm telling the CPU, even if it event discard this source. You got what I'm saying? This is the meaning of you disable, or you turn it on, right? So let me say it again. In maskable interrupts, guys, you can enable or disable these interrupts. And if the interrupt is enabled, every time there is an event coming from this interrupt source, right, you are gonna run the corresponding subroutine, right? But if you disable the interrupt, so that means you discard. Discard means I'm not gonna run, even if there is an event, microprocessor is gonna discard it. So I'm not gonna serve this interrupt until you enable it, right? Until you enable it. Anyway, so, and actually most, no, actually all the interrupts we have are maskable, except only two or three are non-maskable. And even the non-maskable here are not general purpose. They are used for a specific purpose, like reset. So reset is an interrupt, right? And this one is only used in case if you make a reset. So they are very few. They are not general purpose. That's why all my focus will be on this one, right? So here's for the maskable interrupt, the program can ask the CPU to respond or ignore or discard the interrupts. Okay, interrupts can be enabled or disabled as explained. CPU does not execute the interrupt subroutine if the interrupt is disabled. That's what. So you have to write an instruction, as I'm going to explain right now, to enable or disable an interrupt source. Okay. For non-maskable, you cannot disable, like reset. Can any, by common sense, in case of reset, can I turn reset off? So if you press reset, the computer does not reset? No. So that's why, anyway, so that's why all my focus will be on only maskable interrupts here, okay? Because just one or two, and it's used for a specific function, but this one is general. You can use it for anything, okay, guys? So now, based on what I explained right now, I need to explain if you want to enable, or now you should understand, guys. Number one, we have more than one interrupt sources. I told you we have 18 or maybe 20, right? And this may be different from one processor to another. But anyway, we have many or several interrupt sources, right? Every source you can enable or disable, right? So now I'm going to explain how I can enable or disable interrupts, right? What for sure you have to write instructions for sure, but what are what's the instruction I have to write? That's what I'm going to explain right now. So here I'm going to explain how can you enable or disable. You already understand if interrupt is enabled what it means. You also understand if interrupt is disabled what it means, right? So let me start. How can you enable interrupt or disable it, right? So here, look here, guys. There are two level of interrupt enabling capability. Two level, okay? And to enable interrupt, you have to enable the two levels. I'm gonna tell you. Let me finish. But for now, there are two levels, right? And for an interrupt to be enabled, you have to enable the two levels. The first level, we call it global masking. The other one is called local, right? So what you mean by global and local? What are these words? Global means it's just one key or one switch for all interrupts. That's why I call it global. This one we call it local. We use the word local because here we have one switch or one key to enable or disable interrupts, right? This is not a physical switch, guys. This is just one bit. You put 1 or 0 to enable or disable, right? So I'm going to explain right now. So here local means, so here every interrupt source has one bit to enable or disable, but here this is global for all of them only. That's why this one we call it like a master key. This is like a master key. Let me finish and then it's going to be clear now, okay? So let me tell you how it works. Look here, guys. You remember the CCR flag, right? I explained the C flag, V flag, Z flag, N flag, and so on. And I told you we have what we call I flag. I flag here means the interrupt flag, okay? This I flag is used here, right? So how it works, I'm going to tell you how it works. Look here, guys. When you want to disable or interrupts, when none of the maskable interrupts are desirable, the processor can disable all of them by setting the global flag. That means, look here, guys, very easy. If I put here in this bit, if I put 1 here, right? That means all the interrupt sources are disabled. Microprocessor is not going to respond to any interrupt. All of them are off. All of them are disabled. Is that okay? If you put 1. Okay. How can you put 1? You have this instruction, SCEI, or you can use OR operation. So you can use this one or this one to put 1 here so that you can disable all interrupts. Okay? Now, please don't use this instruction because when you connect the Dragon board to your computer, the computer is communicating with the Dragon board using interrupts. So if you use this instruction or this instruction, you are going to receive an error message telling you that I'm not able to communicate with your board when you disable interrupts, right? Because they use interrupt in the communication. Anyway, so again, if you want to disable all interrupts, guys, just to put 1 here, and then all of them are off, regardless of the local bit. If the local bit is saying this enable or this, regardless if this one That's why this one is called a global, or this is the master key, right? So if you put one here, all of them are disabled, regardless of this one. I'm not going to look at this one. Just if this one disabled, all of them are disabled. Is that okay? Now, if I put here 0, does that mean all of them are enabled? No. If I put here 0, that means I'm going to go now look at the local bit. Every interrupt source has 1 bit, right? To enable or disable this interrupt source, right? So that means if you put here 0, that means I'm gonna move to the next level. That's why here I'm telling you we have 2 levels, right? I'm gonna move to the next level so that for every interrupt source there is 1 bit. Again, you can use 1 or 0 for enable or disabled, right? So I'm gonna check. If you enable this local or this interrupt source, I'm gonna serve it. Otherwise, I'm gonna ignore it. Okay. Any question, guys? Is that okay? So how can you clear this bit? Okay. We clear this bit by you clear this bit using CLI, or you can use AND. You can just use CLI. We use it all the time. It's okay. So this one is gonna put 0 here so that we can go to the next one, right? And every interrupt source, guys, should have 1 bit. So now I'm not gonna give you the details now. So later, but at least now you know, for every interrupt source, you have to ask me, what is the enable bit? You told us every interrupt source, there should be enable bit. Yes, right? But the location of this bit may be different from one source to another, right? That's it. But all of them are the same. All of them should have 1 bit to enable or disable this interrupt source for each interrupt source, okay? So here, if I want to express what I explained right now using switches, again, don't be confused, guys. We don't use physical switches this way. I'm just to understand the idea. I think someone left me in chat. When is the project due? I haven't been able to find information about that. Okay, for the project, guys, don't worry about the project. I usually delay it until the exam week, right? So you have until I'm gonna give you like sign up sheet during the exam week. To if you want to do it earlier, if you want to do it in the last lab, so you have 2 options. First, you can do it in the last lab, Thursday, the last Thursday in the semester, or I can delete more. I just want to give you more time to do good projects. So don't worry about it. I'm flexible. I'm gonna give you as much time as I can. So don't worry. I'm gonna talk about it. Okay. So now, what I'm saying now, what I explain right now, I wanna explain the idea using switches. But actually, we don't use the switches. We just instead of a switch, instead of a physical switch, we use like just 1 bit, put 0 or 1 for enable or disable, right? So if I want to display what I explained right now using switches, I can do something like that. Look here, guys. We have different interrupt sources. It's like we have a switch for every, this is one source, and so on. Again, a switch here is 1 bit, 1 or 0 to open or close, okay? It's not a physical switch, just to make sure it's connected or not. Also, we have here I bit. This is the I bit. So I bit here either open all switches or connect all switches, okay? So now, what I want to tell you here, guys, if there is interrupt here, in order to trigger interrupt, you have to close the circuit. In order to trigger interrupt, you have to close the circuit. In order to close the circuit, you have to enable the local bit, right? This is number 1. Number 2, the global bit also has to be enabled, right? This one, so that you close the circuit, okay? In other words, if the global bit is disabled, so all of them are open, so it doesn't matter what you put here. If you open or you close, it doesn't matter because you opened all of them here using the I bit. Okay, guys. So let me tell you the summary of now, guys. The summary is okay. If the global interrupt mask bit I is disabled, and I told you disable means you put 1 here using SEI instruction, right? If you do that, that means all interrupts are disabled, right? That's okay. But if you put 0, that doesn't mean all of them are enabled. Doesn't mean, right? An interrupt is enabled if both, right? The global bit is enabled by putting 0 or CLI, right? Also, you have the interrupt enable bit. Every interrupt should have one bit. As I told you, every interrupt source should have one bit. Also, this one has to be enabled. Okay. So summary, in order to enable interrupts, guys, you have to write two instructions. You have to write two instructions. You have to write CLI to close all these switches, right? Number two, you have to write one instruction to write 1 or 0 as I think one for enable. I'm going to explain later what you have to write, but you have to, there is one bit. This bit is one bit in a register. This bit should enable every source. So now you have to write these two instructions. Okay. Any question, guys? Okay. So that's why I'm telling you, once you understand the story, it's very easy. Why? Because for any interrupt source, guys, you have to use CLI, right? The only difference is where is the enable bit. One time this enable bit in a register called whatever. Okay, for the other source it's going to be different name. That's it. But it's everything is the same. But the location of this bit is different from one interrupt source to another. Is that okay? Now I want to move to another topic or another issue here. Okay, there is something also we call it interrupt flag bit. So again, I finished. Don't be confused. I finished now. How can you enable or disable? Now I'm moving to another thing, right? Related also to programming. There is something called interrupt flag bit, right? So what this means, and how I'm going to use it in programming, how it is useful. That's what I'm going to explain, right? So let me ask you a question. How to request interrupt from the CPU? You told us this interrupt is requested using hardware. Is that right? Yes, that's what I said. So it's a hardware request. So how this is done? How this is done? I'm gonna tell you how it is done. Look here, guys. Every interrupt source should have one bit, right? This bit is called interrupt flag bit. Flag. Okay, so every interrupt source has one bit. This bit we call it interrupt flag bit, right? So that if one interrupt, so this is one source. So this is coming from timer system. This is coming from analog to digital. This is coming from another device. This is multi-sources, different sources. Okay, so if this device wanna trigger interrupt, all what this device has to do, it has to put one here in this bit. Once it puts one here in this bit, hardware bit, right? So this bit is gonna send a signal to the hardware so that for sure if the interrupt is enabled, this is exactly how it works. So if the device wanna trigger interrupt, right? So all what it has to do just to put one in an interrupt flag bit, right? Just to put one here. Once you put one, if it is enabled, this one is gonna go through the hardware to tell the CPU trigger interrupt. You got what I'm saying? So okay, it's like, guys, you know how I when in person lectures, you know how I used to teach this part. Okay, I used to tell students, okay, now if I am teaching a lecture and you want to interrupt me, what would you do? Raise your hand, right? If it is in a lecture, or in our case here in the Zoom lectures, if you want to interrupt me right now, what would you do? Unmute your mic and talk to me, right? So in this case, I have to stop and listen to you, right? This is exactly what happens here. Now CPU doesn't know if there's interrupt or not. So if you want to interrupt your instructor or your professor, you have to raise your hand, right? To interrupt the professor. You want to talk, okay? Same thing here, but for sure these devices don't have hands. And instead of hands, just one bit. So if this device if this device want to trigger interrupt, just to put one here in this bit, right? So once you put one here, you are and for sure if it is enabled, you are requesting interrupt. Is that okay, guys? So who is that clear here what I'm saying? So now every time a device when a request interrupt, it has to put one here in this bit. Is that okay? Now if it is enabled, this one is going to go through the hardware to request interrupt, right? Now when a device requests interrupt, right, and the CPU is going to serve the interrupt. Now you understand what I mean by serve, right? So that means this device requested interrupts and I want to serve the interrupt. So I want to execute the interrupt subroutine, right? And I already served the interrupt. Okay. So what should I do now? I have to clear this bit because this interrupt already served. You got what I'm saying? Yes, you have to do that. You have, that is why, listen to me, this is a very serious issue, very important. Look here, guys. That's why in each interrupt subroutine, you have to write an instruction to clear this bit. You got what I'm saying? Makes sense, right? So let me say it again, and if you have any question, you can unmute me. This is how it works, right? Number one, this device wanna trigger interrupt, or any other device wanna trigger interrupt. What it has to do? It has to raise its hand. How this device is gonna raise its hand? It's gonna actually put one here. Is that okay? And if it is enabled, if this interrupt source is enabled, this one is gonna go through the circuit in order to trigger the interrupt or request interrupt from the CPU, right? Once the CPU decide to serve this interrupt, in the interrupt subroutine, you as a programmer, it's your responsibility to write here a command so that you clear this one. You got what I'm saying? So who's gonna put one here in this bit? Who? The device. It's not you, right? So the device is gonna put one here to trigger interrupt. But in the interrupt subroutine, it's your responsibility to write an instruction to clear it because it's already done. I already served it, right? Very common mistake. Very common mistake. You know what is the common mistake? And try to think about it. This device triggers interrupt by putting one here. Is that okay? And now, in the interrupt subroutine, you are supposed to write an instruction to clear this bit. But you forgot to do that. You forgot to put this instruction. Can anyone think what would happen if you do that? If you forgot to write an instruction to clear this one? Okay, so your program is gonna be frozen. You know why it's gonna be frozen? It's not gonna work. I'm gonna tell you why. What happens is, look here, guys. Now this device has to put one here, right? This is the main program. This is the main program, and this is the interrupt subroutine, right? So once this one is one and everything is enabled, so I'm gonna leave the main program. I'm gonna go execute the subroutine, and then I'm gonna come back. Once I come back, right, I'm gonna think this is another interrupt, a new interrupt. So I'm gonna go back and come back. So go back and come back. So it's gonna be all the time. The CPU is gonna be here all the time. So your program is not gonna work, right? I told you guys, your program, it has to be in the main, also in the interrupt subroutines, right? So this is how it is. So your program is go execute something, come back, and then it's gonna stay some time here. There is interrupt, go and come back, spend some time here, go, come back, quickly go and come. This is how it is. But if all the time this one is gonna take the CPU all the time, your program, so that means you are gonna have like continuous interrupts. You got what I'm saying? So let me tell you the summary. Again, for any interrupt source, every interrupt source should have one flag, one bit. We call it interrupt flag bit. Is that okay? This interrupt source, when it wants to trigger interrupt, this one is gonna put one here in this bit. It's not your responsibility. You don't need to write an instruction to do that, right? This is number one. Number two, your responsibility is once we serve this interrupt in the interrupt subroutine, you have to write a command to clear this one because I already served it, right? So to clear this one, right? Otherwise, if you forget to do that, right, you are going to have a continuous interrupt. So the CPU is going to think this is a new interrupt, right? Is that clear, guys? Any question? So that's why I'm saying, once you understand how can you program one interrupt source, all of them are the same. The only difference is where is this bit. That's it. So when I explain one interrupt source, I'm going to tell you this bit is in this register, right? But for the other source, it is in a different register. But in all cases, you have to do this one. You have in the interrupt subroutine, once you decide, once we serve the interrupt, you have to write a command to clear this bit, right? So that you can clear means I already served this interrupt. So maybe the device is gonna trigger another interrupt in the future. Yeah, that's okay. That's exactly what happens. So if your program is working correctly, so this device is gonna put one, right? It's gonna continue one this way until you serve the interrupt. Once you serve the interrupt subroutine has to. This one is automatically, right, done by the device. But to clear it is not automatically. You have to write an instruction to clear it, right? Once I clear it, now it is 0. Yes. So maybe after some time, after 10 minutes, 1 minute, whatever, this one wanna trigger another interrupt. Yeah, it's gonna put 1. Once you serve, you put 0. Yeah, that's how it is. It's all the time this way. This one is gonna put 1, right? Serve, put 0. This one is gonna put 1, serve, put 0, and so on. Any question, guys? Okay. So the interrupt flag bit should be cleared. You have to clear it, right? When the interrupt is served, right? As long as this bit is set, there is an interrupt that's not served, right? So you are gonna have like infinite interrupts, right? So which doesn't make sense, you know. Any question, guys? Okay. So now let me explain here. Now, guys, I'm talking about programming. How I can program interrupts. And you told us, you give us good news, and you told us it's easy once you understand one, all of them are the same. Yes, that's true, right? So the first thing, in order to do programming, you have to enable you have to enable interrupts. And to do that, as I said, you have to write 2 instructions. One CLI here. The other one, you have to write an instruction in order to enable for what we call a local enable bit. Every interrupt source has 1 bit, right? To enable this local interrupt or disable it, right? Number 2, you told us every interrupt source should have 1 bit. We call it interrupt flag bit. And you told me in programming, in the interrupt subroutine, I have to write an instruction to clear it, right? Yes, because I already served the interrupt. That's true. Also, this you have to do in programming, okay? Now, let's come to the next part of programming, okay? Next part of your programming, guys, is I told you every interrupt source has a subroutine, right? So now I told you we have multiple sources. So this is interrupt source 1 should have a subroutine, right? This is, if you have interrupt source 2, it should have a subroutine, right? Interrupt source 3 should have a subroutine, right? So if interrupt comes, this is the CPU, right? If interrupt comes from source 1, I1, I'm going to go execute and come back, right? If interrupt comes from source 2, I'm going to go execute and come back, and so on, right? So now, where is the location of these interrupt sources? Where is the beginning address, right? You remember when you call a subroutine, you have to say jump subroutine keypad, right? And I told you this keypad is going to be replaced by the beginning address 7,000 or whatever, right? And I told you the CPU is going to go to 7,000, execute until it hits RTS, right? That's what we did in the subroutine, until it finds RTS, right? It's the same story here. But now, where is the beginning? Where is your subroutine? Is that fixed place? Fixed? That means there is a certain number here. This one can be in a certain place? No, the answer is no. So look here, guys. You can put this subroutine anywhere in the memory. It's up to you. I'm not going to tell you where you have to put it. You can. This is the memory management is yours. You can manage the memory as you like. Okay. For example, I1, I can put at I1 starting from 7,000. It's up to me. Okay. You can put it anywhere. This 8,000, right? And here, interrupt 3, for example, from 9,000. I can put it anywhere, right? So once the CPU come here, it's going to execute until it hits RTI. Until it hits RTI to return back. RTI, yes. In the subroutine, we call it RTS. RTS, right? Return subroutine. This one is called RTI, return interrupt. So I'm going to execute later how RTI is little bit different from RTS. But anyway, okay. So now you are telling me if there is interrupt from interrupt source 1, right? The CPU is going to go to the beginning address, execute until it hits RTI. Here it has to go to the beginning address, execute until it hits RTI. If the interrupt is coming from source 3, go execute from the beginning address and until it hits RTI. Is that okay? So now the question is, and now I can select the beginning address as I want. Okay, so there's no restriction. Put it anywhere. It's up to you. Memory management is yours. You can manage the memory as you like. However, I have to tell the CPU, right? I have to tell you the CPU where is the beginning address. You understand, guys? Yes. So how can I tell the CPU? CPU, I can put the subroutines anywhere, but I decided to put it in this place or that place. Okay, so how I can tell the CPU? Very simple. What happened is every interrupt source, guys, it has 2 fixed location in memory. Every interrupt source has 2 fixed location in memory. For example, these 2 for location 1, right? So if I decide for interrupt 1, interrupt source 1, right? It has these 2 fixed location, right? So if you decide to put 7,000 here, yes, so you have to write here 7,000 in these 2 locations, right? So if I decide to put this one in 7,000, so I have to put it here. This is for interrupt 2, and this is for interrupt 3. This is your responsibility to do that. This is in order to inform, in order to let the CPU to know, in order to enable CPU to know where are my subroutines. Okay, so all what you have to do, guys, you have to write. Number 1, you can put the subroutine wherever you want, anywhere, right? So no restrictions. This is number 1. Number 2, all what you have to do, you have to tell the CPU where are these subroutine. How? Every interrupt subroutine should have a fixed location, fixed address, and you have to put the beginning address here. And the CPU is gonna go to once there is interrupt from I1, right? The CPU is gonna go to this location. It's gonna get whatever there, and this is the beginning address, right? So this is what you have to do, right? So how can you do that? That's what I'm gonna explain now. Look here, guys. So this address, we call it interrupt vector. So that's what we call interrupt vector. The interrupt vector of each interrupt source should be stored at a predefined fixed memory location. We call vector address. So again, for example, I'm going to give you a specific example here, guys. Look here, guys. This is a subroutine. What you see here. This is interrupt subroutine, right? As you see, this is the beginning address here, 4103, right? And this is the beginning. So the CPU is gonna come to here, execute, and at the end you have to write RTI to return, right? So all what I need only the beginning address, because once you give me the beginning address, I'm gonna execute until I find RTI to return. That's correct, right? So because this interrupt subroutine for IRQ. And I know IRQ should have this location. FF2, FF3, this fixed. This location is fixed for IRQ, right? But this 4103 is not fixed. You can put whatever you put here. You can put this subroutine anywhere, but you have to store the beginning address in this location, because this location is fixed. It's reserved for the so here this is what we call vector address. So the vector address is the location where you store the beginning address. The beginning address itself, we call it interrupt vector for 4103. Is that okay? So this table, if this table goes, look here, guys, we have different sources of interrupts, as I told you this. So we have many sources. We have here IRQ. That's what I'm going to explain in this chapter. We have what real-time interrupts, RTI. We have timer channel 0, channel 1, and so on. we have here serial communication, two serial communication, by the way. One, if you, I think SCI 0 is used by your USB when you connect connect to the Dragon board. We have analog to digital, so we have different sources, as I told you, right? So every source should have vector address, right? Again, vector address mean it's 2 bytes reserved only for this location, for this interrupt, right? So if I, for IRQ, if I want to program RTI, for example, or IRQ, for IRQ, as you see, I have to put the beginning address in this location and next one, right? Same thing. That's why you can see here, this one is decremented or decremented by 2, right? Because every address should take two locations. So RTI is going to be this one and next one. Okay. So that means for every interrupt source, guys, you can put your subroutine anywhere. However, you should store the beginning address in this location. How can we do that? I'm going to tell you how. Look here. The way you are going to do it all the time as follows. Look here, guys. I'm going to say org ff2. Why ff2? Because this is for this interrupt subroutine, IRQ. If you go to the table, IRQ should have this value, right? So I'm going to say org ff2, right? Then I'm going to say after org dc.w, right? And then I'm going to say the name of the subroutine. You can name it any name. So you in your program, you have you are going to make a subroutine. This subroutine, you can call it any name. For example, I call it here IRQ underscore ISR, and then I'm gonna write, and then I'm gonna put it this way. But why you did this way? I'm gonna tell you why. But simply because when, as I told you before, when you put the name of the subroutine here, this one is gonna be replaced by the beginning address, right? So when I say org ff2, and then that means this one is gonna be written in this location, right? So why we have to use org? Because this is a part of the flash memory, right? So when you run your program in the beginning, you burn or you write to the flash memory, right? So that's why I have to use org this way, so that I can write this value in this location in the flash memory. So let me tell you the summary. Conclusion, very easy. Conclusion is, number one, for every interrupt source you are using, you have to use one like this one, right? What is the difference? The difference is you have to use a different, this number can be different based on the source you are using. So for RTI, I'm going to use this one. For timer channel 5, I'm going to use this one. That's it, right? So for every source, you have to use one like this one, okay? This is number one. Number two, also, for any interrupt subroutine, you can use any name, but usually we use like IRQ underscore ISR. You can just use any name, and just put the name here, the name of the subroutine, put it here, okay? So that this address is going to be stored in this location, okay, guys? Anyway, let me finish, and then I'm gonna give you example. You will understand it much better, okay, guys? Any questions so far? Okay, so let me tell you now, programming. What should you do in the programming? Number one, guys, you have to write an instruction to enable your interrupts. This number one. Number two, in the interrupt subroutine, you have to write a command to clear this bit, right? Otherwise, you are gonna have like frequent interrupts. Number three, also you have to tell the CPU where is your subroutine. You can put it anywhere, but just tell me where is the beginning address as I using this instruction. The next thing I want to teach guys right now, there is something we call priority. Just a very easy thing. We still have one minute or so. Just very easy thing. Okay, we have something we call it priority. So what do you mean by priority? I'm gonna tell you. Look here, guys. I told you we have multiple interrupt sources, as you see here. Sorry, where is the table? Yeah. So we have different sources. Okay. So that means it may happen that two sources request interrupt at the same time. For example, maybe at the same time I have interrupt request from this guy, I have interrupt request from this guy, I have interrupt request from this guy, right? CPU cannot execute more than one at a time. Okay, so what should I do? Okay, so now again the problem is now there are 3 interrupts coming from 3 sources at the same time, right? CPU cannot, it has to do one at a time, right? So there should be like a priority. Which one has higher priority? If this one, if IRQ here has higher priority, so I'm gonna execute this one first. So after I finish this one, I'm gonna look at these 2. If this one has a higher priority, so I have to do this one second, right? And then after that, I'm gonna do the last one here, right? So I'm gonna serve everybody, but I cannot serve more than one at a time, right? As long as the interrupts are enabled, I'm gonna serve all of them, but just about priority, which one should be done first. So what is the priority here? Very easy. So the priority here, guys, is fixed. As you see here, a priority is fixed, right? As you see here, the source that come first here, in the table should have higher priority than other sources. That means this one, if this one comes with this one, so this one first, this is second, right? Also, I'm done. Just also, if number 7 comes with this one, right? So this one first, this is second. So whoever comes, look at the arrow here, guys. Whoever comes here in this one has. Anyway, I'm gonna continue this topic next time, guys. Any question? Okay, guys. Thanks. Bye.
Thank you.
Thanks, guys.
Oh, I have a question.
Yeah, sure.
So I was looking through the notes. I think it's from last lecture, and I wanted to ask about some of the C coding
Okay.
for for as far as like activating the RGB for
Okay.
a C.
Can you?
I didn't really see it in the notes.
Okay. Can you send me an email and we can set time and we can you can set time. We can set time and I can talk to you Zoom, right? Okay, and I can answer all your questions. Okay, just send me email, and I'm free today evening or maybe tomorrow also. I'm free. Okay.
Nice. Sounds good.
Okay.
All right.